Hey everyone. So last time we started with this whole idea of DC modeling, reinterpreting IVSB and CCB to construct some circuit model of a converter that doesn't include all the switching actions. And today, I wanted to, bring in the idea of loss into these DC models and really show where the DC modeling might actually give you some insight into how converters operate with losses. So let's just get right into it. And I wanted to start with a boost converter. Mostly because, if you remember, the conversion ratio of a boost is 1 over d prime. And if you plot this as a function of d, you notice that there is a pole at d equals 1, right? So it shoots up to infinity, right? So it starts at 1 and then shoots up to infinity, right? And the ideal model tells you that you can get infinite gain with a boost. However, we're going to see quite easily with this concept of DC modeling that this just is not possible at all. So let's draw what a boost is. Right, so we have our input and an inductor, a switch. So I'm going to be using a MOSFET and a diode, although, again, you can construct a boost with 2 MOSFETs, whatever you want. I'm just going to use a diode for argument's sake, right? Just to see how the straightforward loss with these elements works out. So what do we got? We got VG. We have L, right? And we can define the voltage VL. We have our MOSFET MS, let's say, and we have our diode D, we have our cap C with the current flowing in this direction. We have our load and the output voltage. And let's just let's specify what the losses are. So we're going to say that MS has some on resistance. So we're only going to consider conduction losses. The main switch, the transistor, is going to have some on resistance, let's say R on. The diode is going to have a forward voltage drop of VF. And the inductor is going to have some resistance, some DCR of RL. Right? And I'm not going to specify what they are exactly. I'm not even going to specify the switching frequency, because this is kind of all you need to know to gain insight into what's going on. So we'll do it as we normally do it, which is by drawing the converter in 2 switching states. So in the first switching state, between 0 and DTS, the main switch is on. And in the second state, between DTS and the end of the switching cycle, the diode ends up being forward biased, right? The inductor forces its current through the diode to turn it on, and you send power to the output. Great, so in this state, we're going to include the losses, right? So we have the inductor resistance, and the resistance of the MOSFET, right? And then we have the output. And then over here, in the second state, we have the input, the inductor resistance. The MOSFET isn't on, the diode's on, and it has a forward voltage drop of VF. And then we have the output. Great. So let's just label some stuff so we know what's going on. We have L, VL, RL, R on, L, RL, VL's in this direction, VF, and then our load, we can draw the capacitor current as we usually do. This is the output voltage, and this is the input. And from here we can start writing our IVSB and CCB equations along with our input equation, right? So we're trying to model also the input behavior of this converter, what it looks like when we attach the converter to a source. So let's do it. So we have IVSB, which says that the average voltage applied to inductor over 1 switching cycle is equal to 0. If we do it this quick way that we've been doing it recently, we just have D and the voltages across the inductor in the first switching cycle, right? So we have VG minus, well, we know that actually IL flows through this loop, right? The inductor current is flowing through this loop, so we must have a voltage drop across this resistor and a voltage drop across this resistor. So we have minus IL times RL minus IL times R on, right? And that's it. In the second switching state, we have D prime times, well, on one side is VG minus, well, IL again flows through this loop, so IL minus IL times RL, minus the forward voltage drop of the diode, minus VF, and then minus V out. And that's equal to 0. And let's just simplify it a little bit. So what do we have? We have VG in both switching states. So we have VG, D plus D prime is 1. We have RL times IL in both switching states. So that must also be IL times RL. We have D prime, or we have D times IL times R on. We have D prime times VF. And then we have minus D prime times V out, and that is equal to 0. And that's how we'll leave it for now. Great. We also have capacitor charge balance, which again says that the average current applied to a capacitor over one switching cycle is equal to 0. And if we do it in this quick way, where we have D times, well in this state it's just minus V out over RL, R load, sorry. And then in the second switching state we have IL flows into the cap and the output current flows out of the cap. So we have IL minus V out over R load. And again, simplifying this, well, we have V out over R load in both switching states. D plus D prime is 1, and we have only IL in the second switching state. So we have, in the end, D prime IL minus V out over R load is equal to 0. And then finally, we have the input equation, right? So the average input current is equal to D times IL in the first state, right? IL flows out of the input in the first state, and it flows out of the input in the second state. And that's just equal to IG, which means that IL is equal to IG. So the inductor current is the input current, as you can expect, considering the inductor is connected directly to the input. Perfect. Now, what do? Well, we use these three equations to construct loop equations, right? So we have a KVL here, we have a KCL here, and then we also have some kind of KCL, right? Something relating currents. So using these three equations, we can construct loops. So the first equation, what did we have? We had VG, let's just look at it again, VG minus IL times RL minus D prime, or minus D IL times R on minus D prime VF minus D prime V out. So minus IL times D R on minus D prime VF minus D prime V out. That's equal to 0. So how do we interpret this? This looks like a loop, right? A KVL equation. And it represents, the inductor. This represents the inductor. So you can imagine in this loop, IL is flowing, right? So we have a voltage VG. And this actually shouldn't be an independent voltage source. It should be dependent because this loop represents the inductor current. So the only non-dependent variable really is the inductor current IL because it exists in this loop. And everything else depends on stuff in other loops. So we leave this VG as a dependent current, as a dependent voltage source. Then we subtract IL times RL. So there must be some resistance here, right? IL times RL represents a voltage drop. This voltage drop, right? And then we have another voltage drop, right? D times R on. This represents an effective resistance of D times R on. Right? We're multiplying D times R on by IL to get a voltage drop. So if you want to think about it in a different way, again, we have IL flowing through it, so that means we can represent this D times R on as a resistance of value DR on. Then we have minus D prime VF. This is a voltage source. It's actually an independent voltage source because it's just some loss. Right, it's not a state variable, it's just a loss variable. So we leave it as an independent voltage source. The other state variables, i.e. the input voltage, the inductor current, the cap voltage, those are all dependent variables, we can say. And then finally we have, again, a dependent voltage source, D prime VF. And this is our loop for equation 1. And we can do the same thing for equation 2. Right, what is equation 2? Well, it's the CCB equation. And it says that, we can just go back here, it says that D prime IL minus V out over R load is equal to 0. So D prime IL minus V out over R load is equal to 0. Well, what does this look like? Well, it's saying, this represents, again, our capacitor, right? Some imaginary capacitor in this loop. And it's saying at this node, you could say we have d prime times IL flowing in, and we have V out over our load flowing out. So this represents our output resistance, right? Our load resistance, V out over our load. We know that V out is across this capacitor. That means that if we're drawing this V out over our load out of this node, then that means there's a resistor there, right? And then we have our dependent current source, right? D prime times IL, right? IL lives in this loop. So the current in this loop depends on the current in this loop. D prime times IL. Cool. And then finally we have our third equation. Our third equation is simply the input equation. And all the input equation says is that Ig, the input current, is equal to the inductor current, right? So again, this equation represents our input. So that means our independent source is our input voltage, right? And what comes out of it must be the input current, Ig, and that is equal to some dependent current source, IL, right? So we know that the current drawn from the input is equal to the inductor current. So now we have our three loops. Sometimes there'll be more for these simpler converters where there are a few elements. There'll typically only be three, but if you have more inductors, more capacitors, you're going to have more equations, meaning more loops. So we have to put these things together, right? And you can kind of see how it fits. This is the output. This is the input. And this thing is the intermediate. So I'll just line those things up in that fashion, right? And then we can figure out how to turn this into a circuit with transformers, right? So we have VG, and again we have RL, D times R on, D prime VF, and D prime V out. And then finally our output is D prime IL, and the load resistance, our load. So now the challenge is, how do we turn this into transformers? Well, first, we want to do the easy stuff first. We can notice that this ratio between the input voltage and the inductor current is 1, right? You just see them copied. That indicates to me instantly that the conversion ratio, or the transformer turns ratio, the DC transformer turns ratio, must be 1-to-1, right? Because there's no change in the voltage across this transformer, right? Or what will be a transformer. So I think pretty confidently we can throw in a 1-to-1 transformer. Again, we indicate that it is a DC transformer with this line through it, and it's 1-to-1. Perfect. Right? And then we have our second loop. And then we have the second problem, right? So RL, DR on. And we have our second transformer. So going back to what the transformer turns ratios, or how they relate to the voltages and currents, we have V1 over V2 is N1 over N2, and I1 over I2 is equal to N2 over N1. Incidentally, this means that R1 over R2, or the resistances you see at the terminals of the transformer, is actually related to the square of the ratio of the square of the turns ratio, right? N1 over N2 squared. So using this voltage ratio, or this voltage turns ratio, we can figure out what the transformer turns ratio should be, right? So on this side, V1 you could say is D prime. And on this side, the voltage is V out, right? So D prime V out and V out. So just plugging that into here, V1 is D prime V out. D2 is simply V out, and that is equal to N1 over N2. Simplifying, we can see that D prime is equal to N1 over N2. And to make it simpler, we can just say N2 is 1. That means that N1 is D prime. So turning this into a transformer, what do we get? We get a DC transformer with turns ratio D prime to 1. and R load. Perfect. We're there. We've got our circuit. And now we can simplify it super easily, right? In one step, basically. So knowing we can move elements through transformers by taking into account the turns ratio of the transformer, we can simplify this equation or this circuit into a single loop, right? We can do that by bringing this voltage source VG into this loop and by bringing this load resistance, R load, into this loop, right? So we're kind of bringing the external things into our central loop. It's easy over here, right? We have a one-to-one transformer, so we can just instantly bring this voltage source into this loop. Right, so we have VG, RL, DR on, D prime VF, sorry, D prime VF, and then we have to bring in this resistance. So again, how do we do this? Well, we have to multiply, given this equation over here, we want R1. So to get R1, we have to multiply R2, which is our load, by our turns ratio squared. Meaning, we have a resistance over here, which is D prime squared, our load. And now this looks incredibly simple, right? Just knowing first year circuit theory, you can solve this, right? It's just a voltage divider. We can figure out what the output voltage is simply by doing a voltage divider, right? We can just say that, again, this actually isn't, sorry. This is actually D, right? This voltage here is D prime V out. So we have to keep that into account, right? The voltage across this effective resistance, D prime squared R load, is actually D prime times V out, right? And we know that IL flows through this loop, IL. Right? That's what we've determined from before. So let's bring this to the next slide and solve it in one go. So we have VG, RL, DR on, D prime VF, and D prime squared R load. And that should give us D prime V out. So, how do we solve this? Well, we know if we want this voltage from this voltage, it's basically just a voltage divider, right? So we know that D prime V out should be equal to VG minus D prime VF, right? So we're just, I'm grouping this voltage with this voltage, right? I'm just sliding this through. You're allowed to do that, right? And what we get is the effective voltage, the sum of these two independent voltage sources, that's why I'm doing it, is equal to VG minus D prime VF. And then we multiply this voltage by the voltage divider, right? So we want the voltage across this resistance, D prime squared R load. So we just use the voltage divider equation. D prime squared R load over D prime squared R load plus RL plus DR on. Right, so immediately this looks really complicated, and I'll just do a few more simplifying steps. So what we want from this actually is the conversion ratio. We want V out over VG. So how am I going to do that? I'm going to divide this whole thing by VG and bring it over to this side, right? And I'm going to divide this side by D prime and bring that over to this side. Doing that, we get V out over VG is equal to, well, 1 over D prime. I'll just leave that out front. And then in this bracket, we have 1, because we divided VG out, minus D prime VF over VG, right? And then times this voltage divider, D prime squared R load over D prime squared R load plus RL plus DR on. Okay, so what does this show us? Well, something very interesting happens. 1, this is the ideal conversion ratio for the boost, right? The ideal conversion ratio for the boost is 1 over D prime, and that we see that immediately over here, right? It's something that is, we multiply the ideal conversion ratio by something to achieve the non-ideal conversion ratio. So this thing is the non-ideal conversion ratio. It's a function of D, it's a function of the losses, the load resistance, all this stuff. R on, VF, RL. It's a function of all that stuff, right? And it turns out it's simply the ideal conversion ratio, right? 1 over d prime times something. It turns out that something is actually a representation of efficiency, right? So this extra stuff, all this stuff, represents how much our output voltage has decreased with the inclusion of losses, which is somehow a representation of efficiency. This thing is an efficiency equation. Turns out it's a function of D, it's a function of the load resistance, right? As we increase the load, we're going to change the conduction losses. It's a function of R on, it's a function of VF, and it's a function of RL, right? All the losses. So that's kind of a really powerful thing, right? We can use this DC modeling to find an equation for efficiency considering only conduction losses. And it turns out that the non-ideal conversion ratio will always be, you can always break it down into something that is the ideal conversion ratio times something. That's something being the efficiency. And we should notice a few things about this efficiency equation. One, we have a 0 in this efficiency equation, right? We have a 0. Right, the 0 is 1 minus d prime VF over VG, right? So somehow, if we choose a specific D, then the efficiency will be 0. Now we have to think about that a little bit. Does it really make sense? We'll get to that. And secondly, we basically have a voltage divider, which turns into something interesting, right? So if we actually bring this d prime into here, right? What do we get? We get d prime, our load, right? I'm just kind of mashing it together to illustrate something, over d prime squared, our load, plus RL, plus dr on. Now, if d prime equals 0, in other words, d equals 1, this tends to 0. This goes towards 0. So as you push the duty ratio with losses in a boost, you don't get infinite, it tends towards 0. So let's just draw this out. Let's just draw out this non-ideal conversion ratio. And this is by no means an exact drawing, but M non-ideal. It's a function of D, blah, blah, blah. It's a function of a whole bunch of stuff. So normally, this is d equals 1, say it's d equals 0.5, and down to d equals 0. So normally, the conversion ratio for the ideal, so let's just use green. So M ideal, d, which is 1 over d prime, looks like this, right? It goes up towards infinity. However, we noticed a few aspects when we included losses. So what do we notice? Well, we notice a couple of things. One, we noticed that there's a 0 somewhere, and then we also noticed that when d equals 1, the conversion ratio tends to 0. So again, this is just a drawing, but we know somewhere over here, the conversion ratio tends towards 0, right? And there's some maximum somewhere. You can find the maximum. I'm not going to spend the time doing that. But then we also have the situation where we have this 0, right? So 1 minus d prime VF over VG. So when does 1 minus d prime VF over VG equal to 0? Well, it's when we have this situation, or when d prime is equal to VG over VF. So will this always occur? Not necessarily, but it could occur. Right, it could occur. So let's just imagine it does somewhere over here. Right, so below this point, the efficiency would actually be negative, and then eventually goes up, reaches some maximum, and then tends back down towards 0. So again, the ideal boost doesn't exhibit this behavior. But if you actually try to build a boost, there's going to be some losses, and you're going to see that there's some maximum conversion ratio that you can achieve. And it's nowhere near infinity. Maybe it's like 3 or 4 or 5 or something. Typically, people end up coming up with new topologies to achieve higher conversion ratios, either using transformers or using some modular design, and we can stack a bunch of things together, stack a bunch of voltages together. But in reality, you're never going to get like a conversion ratio of 100 from a standard boost. It's not gonna happen. Additionally, what does this mean? What would this negative efficiency mean? Or this negative conversion ratio, or whatever you want to say. This negative, can this even happen? Can you have this negative conversion ratio for the boost? Well, no. You're never going to invert the output voltage. Really what's happening is that at this situation, the diode just never turns on. What's happening here is the diode is not turning on. Right, that's important. That means that like this model eventually does break down. Think about how we constructed this model. We just assumed that the diode will turn on and it's some constant voltage source. That isn't really how diodes work, right? Diodes have to be forced on. You have to inject some charge into them before they can actually conduct current. And you have to exceed some threshold voltage, the VF. If you don't do that, then this circuit isn't going to operate and this model will fall apart. So definitely be careful when using DC models. Like, don't look too deep into it. If you see some crazy stuff happening, like negative efficiency or negative conversion ratio for something that should only produce a positive output voltage, think about what's going on, right? Think about, does my model make sense? Does thinking about the circuit in this way make sense? Maybe it does. Maybe some crazy stuff's happening and you've discovered something new, or maybe, the model just doesn't work. Cool, so this is just an example of incorporating losses, and maybe in a tutorial we'll go even deeper and do a more complex example. Thanks.